When we build a bridge, we build trust between cities, communities, and lives. But when a bridge fails, that trust collapses often with devastating consequences. In this video, we examine some of the most catastrophic bridge failures ever recorded, events that shocked the world and changed engineering forever. Let's begin with the tragic collapse of the Tacoma Narrows Bridge in Washington, USA. Completed in 1940, it was one of the longest suspension bridges of its time. But just months after opening, powerful wind-induced oscillations caused the structure to twist uncontrollably. Despite no loss of human life, the dramatic footage of the bridge, wobbling and breaking apart, became a case study in engineering failure. The cause? Aerodynamic instability, a lesson that rewrote bridge design manuals worldwide. Next, we traveled to Minneapolis, Minnesota, where on August 1, 2007, during rush hour traffic, the I-35W Mississippi River Bridge suddenly collapsed into the river below. 13 people lost their lives and more than 100 were injured. Investigators found that a design flaw in the gusset plates, though small, but critical connections combined with added construction load, caused the bridge to fail. This incident raised urgent questions about aging infrastructure in the United States and the importance of proper maintenance and inspection. Bridge failures are rarely caused by a single mistake. They're often the result of multiple factors: structural fatigue, poor design, lack of maintenance, or even natural disasters. Let's turn to the Quebec Bridge in Canada. It collapsed not once, but twice during its construction in the early 1900s, claiming the lives of 88 workers. The first collapse was due to underestimating the bridge's weight. The second was caused by a miscalculation during lifting. It was one of the deadliest construction accidents in history and remains a painful reminder of the cost of engineering oversight. As we reflect on these disasters, it's important to recognize what they taught us. Engineering is not just about strength. It's about precision, understanding forces, and predicting the unpredictable. Now, once the first signs of structural wear and stress begin to show on a bridge, engineers usually carry out close inspections. These inspections include ultrasonic testing, X-rays, and load assessments to determine if the bridge can still carry traffic safely. Unfortunately, in many of these failures, such checks either came too late or were not followed by timely repairs. Take, for example, the Tacoma Narrows Bridge, collapse in 1940, one of the most studied failures in civil engineering history. The bridge famously twisted and buckled due to aeroelastic flutter, a phenomenon no one fully understood back then. The collapse was captured on film, and even today, it's a core case study for engineering students worldwide. That tragedy didn't just bring down a structure. It reshaped how engineers design bridges to withstand wind forces. Another example was the Quebec Bridge disaster in Canada. It collapsed twice during its construction. First in 1907 and again in 1916, causing over 80 fatalities. These weren't just construction errors. They were rooted in design flaws, poor communication, and underestimating the weight of the structure. It's a chilling reminder that assumptions in engineering can be deadly. But bridge collapses are not only from design flaws. Sometimes, external forces like earthquakes, floods, or shipping collisions can trigger them. In 2007, the I-35W Mississippi River Bridge in Minnesota collapsed during rush hour. Investigators traced it back to a design flaw in the gusset plates, but also emphasized the excessive weight from construction equipment placed on the bridge that day. The disaster led to a major overhaul in bridge inspection regulations across the United States. In each of these cases, lives were lost, communities were shaken, and billions were spent on recovery and rebuilding. These failures are devastating, but they also teach us. Every collapse becomes a loud alarm to the civil engineering world. Check, inspect, improve. That's why today's bridge engineering involves advanced simulation software, constant structural health monitoring, and redundancy in design. One failure can ripple through an entire nation's infrastructure strategy. As we continue exploring the world's most catastrophic bridge failures, it's important to reflect on the silent warnings that often precede disaster. In many of these cases, the signs were their cracks, vibrations, structural instability, yet they were ignored, misunderstood, or underestimated. Take the Tacoma Narrows Bridge. Collapse in 1940. Engineers at the time didn't fully grasp the effects of wind-induced oscillations. The bridge, often nicknamed Galloping Gertie, twisted and buckled in rhythmic waves until it broke apart. Today, it's studied in engineering courses worldwide as a case study in aerodynamics and design limitations. What failed here wasn't just the structure, but the understanding of how nature interacts with engineering. Another chilling incident was the 2007 I-35W Mississippi River bridge collapse in Minneapolis, USA. A design flaw in the gusset plate's metal sheets that connect steel beams was overlooked for decades. When the bridge was under maintenance, extra weight pushed the structure past its limits. 13 lives were lost. This tragedy taught us that even the smallest, overlooked detail can lead to massive consequences. In the case of the Morandi Bridge collapse in Genoa, Italy in 2018, corrosion, poor maintenance, and aging concrete contributed to a sudden and tragic failure. Over 40 people died when the bridge gave way during a storm. It sent a global message about the cost of ignoring infrastructure maintenance. No bridge, no matter how grand, can outlive neglect. Each of these stories reveals more than just technical flaws. They expose the human factor, decision-making, budget constraints, time pressures, and underestimating risk all play a role. Behind every bridge failure is a chain of choices, some made decades earlier, that ultimately lead to disaster. But from these failures also come advancements. Materials are tested more rigorously. Software simulations now model years of wear and extreme conditions. Maintenance schedules are smarter, and sensors embedded in structures now warn engineers before it's too late. These tragic collapses, while heartbreaking, push the industry toward excellence. They remind us that innovation isn't just about building taller, longer, or stronger. It's about building safer and smarter. Lives depend on it. So next time you drive across a bridge, remember, every beam, every cable, every bolt carries the weight of both its physical load and the lessons of history. It is the duty of every engineer, planner, and government to uphold that legacy of vigilance and responsibility. In our final part, we'll look at how new technologies like AI, drone inspections, and smart infrastructure are transforming how we design and maintain bridges around the world. Stay with us.